In this video, I'm going to talk about divisibility. Divisibility is a very common theme in a lot of math competition problems, and I'm going to try to explain the definition as well as some of the basic properties. We say that an integer a, where a is not equal to 0, divides an integer b if there is an integer c such that b equals ac. We could also think of this as a being a factor of b and b being a multiple of a. We denote that a divides b using this notation. The first property that I'll discuss is the following. If a divides b, then the absolute value of a is smaller or equal to the absolute value of b as long as b is not equal to 0. The proof of this is as follows. Since a divides b, b equals ac, where c is an integer. But since b is not 0, c can't be 0 either. Since b equals ac, the absolute value of b is equal to the absolute value of a times the absolute value of c. Since c is not 0, the absolute value of c must be greater than or equal to 1. So the absolute value of a times the absolute value of c is greater than or equal to the absolute value of a. The second property is as follows. If a divides b and b divides c, then a divides c. The proof for this is that since a divides b, b equals ax, where x is an integer. Likewise, since b divides c, c equals by, where y is an integer as well. By substituting b equals ax into the second equation, we get c equals a times xy. Since x and y are both integers, their product is also an integer. It follows from c equals axy that a divides c. The third property says that if a divides b and c divides d, then ac divides bd. The proof is as follows. Since a divides b, ax equals b, and since c divides d, cy equals d, where x and y are integers. Multiplying these two equations together, we get bd equals ac times xy. Since x and y are both integers, the product is also an integer. So it follows that ac divides bd. The fourth property says that if a divides b and a divides b plus or minus c, then a divides c. The proof says that since a divides b, b equals ax, and since a divides b plus or minus c, then b plus or minus c equals ay, where x and y are integers. Substituting the first equation into the second, we get ax plus or minus c equals ay. By moving ax to the right side and factoring, we get plus or minus c equals a times the quantity y minus x. By moving the plus or minus sign to the right side, we get c equals a times plus or minus y minus x, which leads to a divides c, since y minus x must be an integer. The fifth property says that a minus b divides a to the k minus b to the k for all positive integers k. To prove this, we can factor a to the k minus b to the k in the following form. Similarly, we can prove the sixth property, which says that a plus b divides a to the k plus b to the k for all odd positive k. We let k equals 2n plus 1, where k is a non-negative integer. This way, k will always satisfy the criteria of being odd and positive. By substitution, a to the k plus b to the k equals a to the 2n plus 1 plus b to the 2n plus 1, which can be factored in this way. The second factor will always have terms alternating in sign.